morning, calculus students. So in this video, I want to review how to determine continuity and differentiability in a piecewise function. So we already looked at how to do this on a graph. So looking to see if it's continuous or differentiable, and with more simple equations, but more than likely you're going to see a piecewise function on the AP exam. And so just a reminder, to check if something is differentiable, we always have the same steps, or sorry, continuous. So let's review continuous first. So in order to check continuity, there are 3 steps. We need to check, does the limit as x approach c of f of x exist? So let's say we're checking continuity at point C. Then we need to check, does f of c, is f of c defined? And then the last thing to check is that these two things are equal to each other. So does the limit as x approach c of f of x equal f of c? If all 3 things work, then yes, it is continuous. In order to check differentiability, we need to check that the left and right hand limits are the same. So we're going to check that f prime of x from the left equals f prime of x from the right. So this means that the left-hand derivative equals the derivative from the right, if you want to translate that into words. So for each of these problems, they gave you the original function, and I'm just letting you know what the derivative is. So I don't want you to work on finding the derivative. I'm just going to tell you these are your derivatives. Okay? I want you to focus on using these functions to check continuity and to check differentiabilities. Okay? So just a note on this derivative, this says 1/2. So this is a 2 times the square root of x plus 5. And this one is -1/3 times the cube root of x minus 4 squared. So just so you know, that's the derivative. Period 1, we did problem A together, so we'll do B right now. So we'll start by checking if it's continuous. And you can also see I whited out those boxes because they were annoying to me. So first I'm going to check, is this continuous? Okay. So we're going to, we'll see, does the limit exist? So we need to check the limit. Here's step 1. The limit as x approaches -1 from the left of f of x. So -1 from the left would be this bottom function, and that is equal to -1 minus 4 is -3. And then the limit as x approaches -1 from the right of f of x would be the upper function. When I plug in -1, I get 1 minus 1 minus 3, which is equal to -3 as well. So I see that the limit does exist. Then I need to check which is f of -1, which means I would just be plugging into this top function, which I know equals -3. These two things are equal to each other. So limit equals function value, which means, therefore, f of x is continuous. So I do know it's continuous. Just because I know it's continuous doesn't mean I know it's differentiable, so we have to check that. We're going to check if it's differentiable. So let's check the limit, or sorry, the derivative of x to the left, and we're doing this at -1. So instead of writing x, I can write -1 in here. So the derivative of f at -1 from the left. And so that means I'm using this bottom value, so that's to the left. I use the bottom derivative, that's equal to -1. Then the derivative when x is equal to -1 from the right, I use this top function to the right of -1. And that I would also get -1. So because the left and the right slopes are the same and it's continuous, therefore f of x is differentiable. I should add one note. So one thing that you need to check is kind of not only that the slopes are the same, I should add and it is continuous. Because we saw in first period, there can be a special case where the slopes are the same, but it's not continuous. We saw that with this jump. Oh my god, I have so many tabs. Where's my Desmos tab though? We saw this in Desmos. Did I lose it? I don't have it open anymore. How could I have closed my tab? There's Alex. TCMS. This is my last hope. It's on my other page. Yeah, I don't know. Well, whatever. But we saw a special case where the slopes were the same, but it was a jump function. So maybe it looked like this. The slopes are the same from the left and the right, but there's a big jump here, so it's actually not differentiable at the point. That's all I want to say. Okay. Cool. Let's look at one more together. We can do, I'll let you do C because you need to practice your algebra. We'll do D together. A little bit of trig together. So for this one, let's start same way. Check if it's continuous. So we're going to be plugging in, find the limit. So the limit as x approaches 0 from the left of f of x. Left means I use this bottom function. When I plug in 0 into here, I just get 0. Then the limit as x approaches 0 from the right of f of x, I will use the top function. Sine of 0 is also equal to 0. So I know that the limit exists and it equals 0. I also know that f of 0 equals 0 because, again, I would just plug into this function when we have 0. And so, since the limit equals the function value, then I can say f of x is continuous. So it is continuous at that point, 0. Now I need to check if it's differentiable. So f prime of 0 from the left, we'll use this bottom function. F prime of 0 from the left would be 1 minus 0, which is 1. And then f prime of 0 from the right, I will use the top function cosine. Cosine of 0 is equal to 1. So, since the derivative from the left equals the derivative from the right, and it is continuous, then I can say that f of x is differentiable. Woohoo! So I'll let you all do C, and if you don't have it, A on your own. And I will show you how to do example 3A. So we're going to do 3A. There's the bell. School is over. But this video is going to keep going. So this is one of the problems where we have variables, a and b, and we need to figure out the variables that will make f of x differentiable. So essentially, we need to look at f as well as f prime, just like we did in the previous functions, in the previous problems. And since I have two variables and two functions, so let's write that down. So we have two variables and two equations. This should sound a little familiar. We're essentially going to make a system of equations. Okay, so we need to make a system of equations. Okay. So since I'm going to make this differentiable, I also know that this function must be continuous. So if it's differentiable, it must be continuous. So I can start by saying that, so if this is continuous, then I know that the following must be true. So if it's continuous, I know that the following must be true. I know that the limit as x approaches 1, I'm going to choose 1 because of those. So as x approaches 1 from the left of f of x must equal the limit as x approaches 1 from the right of f of x. If it's continuous, that has to be true. So this is the limit as x approaches 1 from the left would be this bx minus 3. And then this is the limit as x approaches 1 from the right would be ax squared plus 1. And I can plug in 1. So when I substitute 1 for x, I get b minus 3 equals a plus 1. Okay. So I have this equation with b and a. I need to use my derivative function to come up with my second equation. So if this function is differentiable, then I know that the following must be true. So if this is differentiable, I know that the following must be true. I know that f prime of 1 from the left must equal f prime of 1 from the right. So f prime of 1 from the left would be this bottom function, which is just b. There's no x to plug into. And then f prime of 1 from the right would be the top function, and I'm going to plug 1 into there. So it's 2a times 1. So now I have this equality that I can plug in over here. So I'm going to plug this in. So I have b equals 2a. That means instead of writing b, so b minus 2a, I'm color coding a little bit, I can write 2a minus 3 equals a plus 1. So this substituted in right there. That's how we do a system of equations. And now I only have one variable. I can solve for a. So subtracting a from both sides, I get a minus 3 equals 1, which means a equals 4. And then if a equals 4, I can plug in over here. Plug in again. And I get b equals 2 times 4, so b equals 8. And those are the value of a and b I need for this thing to be continuous. Okay. So I want you to try the other problems on your own. Sorry, I had a knock at the door. 1 second. Sorry. Okay, so what you need to do is I want you to finish the rest of these examples for your homework. So it looks like you have 2a and c as well as 3b. So you should do those in the end in order for you to check yourself. For 1a, so for 1a you should get continuous but not differentiable. For 2c you should get continuous but not differentiable. And then for 3b you should get a equals 9/14 and b equals negative 27 over 7. Cool. You can do it. And I will see you on Monday.